So this is our first attempt to have a sort of seminar lecture series. I hope it will become a tradition. And I'm happy to have as a first speaker Ben Davison from the University of Edinburgh. So his title for all 3 lectures, because he will give 3 lectures, is Cohomological Donaldson-Thomas theory and nonabelian Hodge theory for stacks. And I understand that the special title for his first lecture is a decomposition theorem for 2 Calabi-Yau categories.
Yes.
So Ben, please.
Thank you very much for the invitation. It's an honor to be speaking in this seminar. And in this first talk, my plan really is to introduce a couple of things, to really introduce cohomological Donaldson-Thomas theory and the integrality conjecture / theorem, and also try to promote the importance of the decomposition theorem inside geometric representation theory and the sort of utility of the decomposition theorem. So yeah, that's the sort of title of part 1 here, or lecture 1. So to give a reminder of the original decomposition theorem, due to valence and Bernstein, Deline and Gabor, we start off by assuming we have a projective morphism of algebraic varieties. And to start with, we're going to assume that X is a smooth variety. So X itself needn't be projective, but it needs to be smooth, and the morphism to Y needs to be projective. And I'm introducing a little bit of notation here. This subscript ver for virtual just means that I shift this cohomologically by the dimension of X. So this is the constant sheaf with rational coefficients shifted essentially so that it's a perverse sheaf, so that it's self-dual under Verdier duality. Sorry, and that's what I'm going to sort of do throughout this talk. So whenever you see that subscript, it just means a cohomological shift by the dimension. Okay, so the actual statement of the theorem comes in 2 pieces, and I want to separate out those 2 pieces. So the first piece tells us the following. The guy on the left, so as another sort of statement of ground rules, whenever I write P lower star, I mean the derived push forward. So this is some object in the bounded derived category of constructible sheaves on Y, and being an object in the derived category, it has cohomology sheaves, so these are showing up on the right-hand side, but also being an object in a derived category, there's normally no guarantee at all that you'll have an isomorphism like this, that the thing will actually be isomorphic to the direct sum of its shifted cohomology sheaves. But the decomposition theorem tells us that under these circumstances, we do get a decomposition of this form.
So what this upper script P on the left, if it's P, what does it stand for?
The math frac P. So that's and I'm sort of going to drop that as the talk goes on, but that's me taking the perverse cohomology sheaves. So these are the cohomology sheaves.
In the T structure, okay.
The perverse T structure.
Okay.
So
just you're talking about more general perversity or just the middle perversity?
Middle perversity always, yeah.
Yeah, thank you.
And the second part says that each of these cohomology perverse sheaves is semi-simple, so a direct sum of simple perverse sheaves. And simple perverse sheaves themselves have a nice description in terms of intermediate extensions of simple local systems on locally closed varieties, but I'm not really going to get much into that. So yeah, like I say, I really want to separate out the 2 statements here. The first is that the thing is isomorphic to its total cohomology, and the second is that each cohomology sheaf is itself semi-simple, so it has a decomposition into simple pieces. So throughout the talk, any complex in any bounded derived category or even unbounded derived category, which is isomorphic to its total cohomology, I'm just going to call split. Of course, we're going to generalize this a long way, but the first generalization is to allow X to be a singular variety, in which case it's fine. There still is a decomposition theorem. It's just that the constant sheaf shifted by the dimension of x is no longer the right thing to take. Instead, one takes, well, the intersection complex. So this is the intermediate extension of the constant perverse sheaf from the smooth locus. So this is some simple perverse sheaf, which in the event that x is smooth, just agrees with this shifted constant sheaf. But if x has some singularities, sort of makes up for those singularities and cooks up a simple perverse sheaf, which agrees with the constant perverse sheaf on a dense open locus given by the smooth locus. Okay, so for this magic object, this intersection complex, if I feed that everywhere into this theorem, the same remains true. So the p lower star of ICX is split and its cohomology sheaves are semi-simple. Okay, so that's the sort of, the origin story. As we get through the talk, it's going to become more and more useful to use a slightly fancier version of the decomposition theorem, which came along later and is part, and a large part, of the whole machinery introduced by Saito of mixed Hodge modules. So my priority here is to not scare away everyone in the audience who has no familiarity at all with mixed Hodge modules. It's very much the philosophy of this talk, and indeed of much of what I do, is that mixed Hodge modules is like, I don't know who to attribute this quote to, but in order to drive the train, you don't have to be able to disassemble it and reassemble it again. You just need to, know which levers do what. And that's the sort of pragmatic approach that I want to take to mixed Hodge modules. But in order to say something concrete, I have this slide. So given X a complex variety, we have this category of mixed Hodge modules, which you can think of as kind of augmented perverse sheaves, in the sense that there's a forgetful morphism from mixed Hodge modules to perverse sheaves. So, and it's faithful. So you should think of a mixed Hodge module as a perverse sheaf plus some extra data. And we're not really going to get into much of what that extra data is. The only important bit, in fact, will be something that's quite easy to get into a single bullet point, which is that part of the data is a filtration on this underlying perverse sheaf given by the weight, called the weight filtration. So this is some ascending filtration of my perverse sheaf, and this is part of the data that goes into upgrading my perverse sheaf to a mixed Hodge module. And like I say, it's really the only bit of data that I'm going to have cause to say much about. And just some definitions. A mixed Hodge module is called pure of weight I if the associated graded with respect to the weight filtration is all concentrated in the ith piece. So this means that the weight filtration, which is ascending, is sort of 0, 0, 0, 0, 0, 0, 0, and then it gets to the ith bit of the weight filtration, and then jumps to be the whole of F, and then stays the whole of F for the rest of time. Yeah, so that's what this means. And if I have a complex of these mixed Hodge modules, I'm just going to call it pure if each of its cohomology mixed Hodge modules is pure of weight matching the cohomological degree, which seems like an odd convention to start with, but how to motivate this? So with this convention, I've frozen. Can I get, can anyone still hear me?
Yes.
Yeah, I hear you, yeah.
Yeah, I think that was something went wrong. With this convention, the singular cohomology of a smooth projective variety is pure because the ith piece is pure of weight I. So that's one way to sort of motivate this slightly odd looking convention. Yeah, so like I say, I want to black box a lot, but in order to get into the black box, I need to be, I need to have some mixed Hodge modules to start with. And these are the ones that we're going to start off our fun and games with. So the constant perverse sheaf on a smooth variety has a lift to a pure weight 0 mixed Hodge module, as does the intersection complex in the event that X is singular. So here are at least some mixed Hodge modules for me to start playing games with. And what are those games? The six functor formalism. So if I have morphisms between varieties, I can take direct images, inverse images, exceptional direct images, exceptional inverse images, Verdier duals, just the whole yoga of perverse sheaves lifts to mixed Hodge modules. So, right, and using it, we can state Saito's version of the decomposition theorem. So firstly, the category of pure weight n mixed Hodge modules on any variety for any n is semi-simple. And here's the bit that starts to look a bit like the decomposition theorem, that if I have a projective morphism, then the direct image along F preserves pure objects. So if we look at this final bullet point, how to recover the usual decomposition theorem here would be, you take your intersection complex, if X is singular, you upgrade it to a pure weight 0 mixed Hodge module, so a pure object in the bounded derived category of mixed Hodge modules. You take its direct image. Saito's theorem tells you that whatever you've got now is pure, which means that, yeah, I need to go forward one, which means that by the next part of Saito's theorem, this thing splits. It's isomorphic to its total cohomology. And what's more, by the first part, this category of pure mixed Hodge modules is semi-simple, so each of these cohomology mixed Hodge modules is a direct sum of simples.
Okay, just finish and then I ask.
Yeah, but really the main takeaway for us is that if I have a pure complex of mixed Hodge modules and I take its direct image along a projective morphism, then this splits in the sense that it's isomorphic to its total cohomology. So this is the kind of Saito version.
No, I mean, for people who like perverse sheaves, there are some of them, but do not know mixed Hodge modules. What's the reason for the upgrade? It's theory or what?
Yeah, so the reason is the following, and this comes much later, as in not during this talk and probably not during the next one either, is that, but I'll say it anyway because it's super important. It's that purity is a local property. So let's say I'm trying to prove some version of the decomposition theorem in a context where the usual standing assumptions of the decomposition theorem just don't hold. So let's say I'm pushing forward a complex that is just not pure, but I still want to show that it somehow satisfies the decomposition theorem, i.e. that the direct image is pure. Or rather that the direct image splits. So one way to show that the direct image splits is to show that I have a pure complex and use Saito's machinery. And that purity is something I can check locally. Checking that something splits isn't something I can check locally. If I have some, if I take the direct image of some complex and I show that on an open cover of the base that the thing splits, that's not enough to get that the whole direct image splits. But if I show that it's pure on an open cover, then because purity is a local property, it's pure everywhere. And so by Saito's machinery, I get that the thing splits. So it will, in the end, be vitally important to use Saito's machinery. Yeah, this point will be revisited if I went through that too quickly for everyone. But it does help, and it is in fact essential to what I'm going to do to use mixed Hodge modules. But like I say, I mean, really all we need to remember about a mixed Hodge module is that it's a perverse sheath that comes with a weight filtration and that they satisfy certain rules, namely Saito's version of the decomposition theorem. And that's more or less enough to get to the finishing line.
And also that the category of a pure with mixed Hodge modules, these are actually it's inside of a triangulated category, but this category is a abelian subcategory. Am I right in understanding?
Yeah, that's right. Yeah, I mean,
But what's the meaning of a split? Split means in the BBD decomposition?
Yeah, sorry, I introduced this. I don't know how standard or non-standard or how much of a clash of notation this is. I just didn't want to keep writing that the isomorphism with the direct sum of the shifted cohomology sheet. So to say it splits means that it's isomorphic to its total cohomology.
I see.
Yeah, complex.
Actually, probably there should be your slides posted in the chat. Lina, did you do that? So then you for example, can look at the convention list. It was on the first slide.
I just did it now.
Okay, please.
Thank you. Okay. Sure. Okay, I'll press on. Okay, so again, sort of fast forwarding to the nonabelian Hodge theory side of things. The thing that people really love to do with the decomposition theorem, at least people who think hard about Higgs bundles, is to work with the induced perverse filtration that you get from the decomposition theorem. So people often don't really spell out how that comes about. So I wanted to spell this out properly. So here's the setup. P is a projective morphism. F is some pure complex. So if you like, just set X to be a smooth variety and set F to math cal F to be the shifted constant sheaf. Then by whichever version of the decomposition theorem you need to use, this thing splits in the sense that it's isomorphic to its total cohomology with zero differential. Okay, so the P lower star F is this guy, which is the target of beta. It's the direct sum of the cohomology sheets. And the truncation of P lower star F is the same sort of direct sum, except we leave out all of the summands past the ith place. And the sort of obvious thing is that there's a morphism going the other way. There's a projection going from right to left, which is a left inverse to this morphism beta. Whereas if you pick X, Y, P, and F at random, it generally won't be the case that this natural transformation from the ith truncation to the whole of P lower star of F will have a left inverse. But the decomposition theorem buys this for us. So we have this left inverse to beta. So when we pass to derived global sections, we get something that still has a left inverse. So in particular must be an injection.
So H is the usual cohomology or what?
Yeah, it's the lower star push forward to a point. Right, so we have this morphism of cohomologically graded vector spaces or cohomologically graded mixed Hodge structures, and it has a left inverse, so in particular it's an injection. And we define the image of this injection to be the ith piece of the perverse filtration with respect to this morphism P. And because the ith truncation factors through the I+1th truncation, you do indeed get an ascending filtration of your cohomology of F this way. Okay, so the decomposition theorem is buying a little bit of what I'm saying at each stage. So in particular, this morphism, which I'm failing to highlight, that is the second equation, is an injection, is bought for you by the decomposition theorem. And that you get this ascending filtration is brought for you by the decomposition theorem. So it's really essential that you have this splitting property. And just some sort of formal odds and ends to add to this discussion. If I have a morphism of complexes of sheaves or mixed Hodge modules, and let's assume that both of these sheaves split when I take their direct image along P, then I get, by taking derived global sections of this morphism K, I get a morphism from the derived global sections of F to the derived global sections of G. But what's more, this morphism respects the perverse filtrations. Because, well, I can take the ith truncation functor applied to the morphism K to get a morphism from the ith truncation of F to the ith truncation of G, and then take derived global sections of that. And that gives me the induced morphism from the ith piece of the perverse filtration on the left-hand side to the ith piece of the perverse filtration on the right-hand side. So it's not difficult and it's not deep, but it's worth pointing out that that perverse filtrations have this functoriality, that if I have morphisms between sheaves upstairs, I get morphisms of filtered complexes when I take derived global sections. Furthermore, if I have some morphism from Y to a Y prime, which is finite, meaning, well, quasi-finite and projective, this is enough to get the derived direct image along Q is exact with respect to the perverse T structure. So again, it's not difficult, it's somewhat formal, that the perverse filtrations defined with respect to P or with respect to QP, i.e. with respect to the base Y or with respect to the base Y prime, are the same. That comes down to perverse exactness. Okay, so that's just a little bit of setup. In order to talk about Donaldson-Thomas theory, or cohomological Donaldson-Thomas theory, I need to say something about vanishing cycles. And again, I'm conscious not only here, not only with mixed Hodge modules, but with this talk in its entirety, of the risk of scaring people away. So how to mitigate that here? So I'm going to introduce these functors of vanishing cycles. But in fact, by the second talk, when we start talking about two Calabi-Yau categories, so things like categories of representations of pre-projective algebras, or Higgs bundles, or coherent sheaves on surfaces, we'll find that the vanishing cycles systematically go away. If you take against them violently, then don't worry. In the end, they will go away. But in order to do cohomological Donaldson-Thomas theory to start with, I'm going to have to say something about vanishing cycles. So vanishing cycle sheaves, in a nutshell, are the sheaves that we put on moduli spaces of objects in three Calabi-Yau categories. So things like categories of coherent sheaves on three Calabi-Yau varieties. And they somehow provide the right sheaf for counting these objects. So they provide a better alternative than the constant sheaf, in a sense that will become a little, hopefully a little clearer by the end of this slide. But this is in italics because it's basically a slogan, which doesn't necessarily have any mathematical content yet. Okay, but here comes the actual definition. I start off with a regular function on a smooth variety X, and I denote by R the inclusion of the preimage of the strictly negative real ray, and by iota the inclusion of the zero locus of F. And here is the sort of quick and nasty definition. The nearby cycles functor is given by first restricting along the strictly negative ray, and then restricting to the zero locus. And then the vanishing cycle functor with this P, the P is there because there's this shift by -1. If the shift by -1 isn't there, then you don't have the P, but also the thing isn't perverse exact. So anyway, this is just some notation. We put a P here to mean that we've shifted in a way that makes this functor exact with respect to the perverse T structure. Okay, so I don't expect actually for this definition to be very illuminating at all, and that's why I'm going to sort of speed through it and get some examples where I hope I'll be able to explain what's going on here. But the first thing to note is that if X is smooth, as we're assuming, and I apply this functor to the constant perverse sheaf, then I get heuristically, I get a perverse sheaf that is supported on the critical locus of this function F, so on the singularities of the preimage of 0. And the sheaf is not just a constant sheaf on that critical locus, it somehow measures how bad the singularities are there in a way that this next example hopefully sheds a tiny ray of light on. So here's the sort of one example that one can actually do by hand. So we start off with X just being the affine line. We pick our function to be x to the n plus 1. So this the zero locus of this is just 0. And and it has a singularity there. If I take the scheme theoretic critical locus of this function, it's not just a point, it's not just the origin, it's the origin with some nilpotent thickening, because the derivative of this function is up to a scalar is x to the m. So there's some sort of singularity here, and the bigger m is, the worse it is. And okay, so from the kind of description of what the nearby cycles functor does, first you consider the pre-image of the strictly negative real rays. So that will look like, this is where I miss having a blackboard. That will look like a sort of like the spokes of a bicycle wheel. There will be m+1 spokes coming out from the origin of rays that get sent to the strictly negative real ray. And then when I look at the origin and restricts there, I just get m+1 copies of the constant sheaf up to a shift. And then because the vanishing cycles are defined via this cone, I take away one copy of the constant sheaf at the origin, corresponding to, well, the constant sheaf on the zero locus of f.
So you denote that Q0 in order to stress that it's a sheaf and not just a vector space somehow, because Q0, not just Q.
Yeah, so Q0 for me means the constant sheaf at zero.
Yeah. Yeah, but actually, I mean, for topologists, there is sort of a simpler description. This is just a formal definition, like from Linus. But
yeah,
if you look for the relative cohomology, then it's kind of it's not that mysterious. So there is a purely topological, but not obviously functorial definition. Yeah.
Yeah. Well, I'm not, I'm not super happy with this slide anyway, because I've defined this functor as a cone, which everyone knows you're not allowed to do. So it's not, yeah. But anyway, the takeaway is that the vanishing cycles functor, I mean, there'll be more takeaway on the next slide, but it's some functor which, when applied to the constant sheaf, tells you how bad the singularities of the pre-image of zero are. And the next example, this again is an example that one can do by hand, but it's sort of at the limit of what one can do without any sort of machinery, just with the back of an envelope. Again, yeah, we let x be now the affine plane, f is equal to xy, then exercise the vanishing cycle functor for f applied to the constant perverse sheaf on x is again the constant sheaf, but just at the origin, which makes some sense, because that is the only piece of the singular locus of the vanishing locus of this function f, which is two lines meeting at the origin. Okay, so that is at least some introduction to vanishing cycles. But I'm basically going to take the same approach to them that I'm advocating for mixed Hodge modules as a whole in this talk, which is that they're a sort of black box, and that there are just some rules for manipulating them, and I'm just going to give you all of the rules that I'm going to use. So firstly, if P is smooth, then by base change, I have this natural isomorphism. So I can do one of two things. I can take the vanishing cycles functor with respect to f, a function on y, and pull back along P, or I can pull back whatever sheaf I started with along P and apply the vanishing cycles functor for the composite function. Likewise, if P is proper, then this thing commutes with push forward. It's exact with respect to the perverse T structure. I think it's the result of GABA. I mean, I should give names for some of these. This one definitely has a name. This is called the Thom-Sebastiani isomorphism. At the level of perverse sheaves, the statement here is proved by Massey. At the level of mixed Hodge modules by Saito. And it tells us essentially that there's a kind of Kunath isomorphism for vanishing cycles functors. In the sense that if f and g were just the zero function, then the vanishing cycles functor with respect to both of them would just be the identity functor. And this would just literally be a Kunath type isomorphism. So it's a generalization of Knuth to the situation where you have non-zero functions. And what's more, and this is again part of Saito's opus, that this functor, which on the face of it is just defined for perverse sheaves, can be lifted to a functor between mixed Hodge modules. Okay, so as I indicated at the start of this talk, I'm kind of obsessed with when direct images split. So let's say we have some f in the bounded derived category of mixed Hodge modules on X. And let's say the direct image along P of f splits. Then I claim that so does the direct image of any vanishing cycles functor applied to yeah, so sorry, there's a typo here. This should be the vanishing cycles functor for the function fp. Okay, so yeah. First off, I can commute vanishing cycle functors past direct images along proper maps. And again, this function is also wrong. This should be the vanishing cycles functor just with respect to f. And then by exactness and by the fact that I'm assuming that the direct image of f splits, I get this isomorphism here. But then, I mean, each one of these summands, even after I apply the vanishing cycles functor to it, is still perverse by exactness. So I've proved that the direct image of the vanishing cycles splits as long as the thing I'm pushing forward splits. Okay, so that's just a sort of example of the way we can play with these general facts. Okay, so as I sort of hinted earlier, the whole thing that I'm up to is proving the decomposition theorem in areas or in contexts where it's not expected to be true. So areas where some of the background assumptions for the decomposition theorem actually fail, whether it be that P isn't actually a projective morphism after all, or that the complex that I'm pushing forward along it isn't pure. So how we do that in this talk is as follows. It's via this notion of morphisms that are approximated by proper maps or by projective maps. So we say that P, a morphism from a stack or a space to a scheme, and we're assuming finite type here, but let's not focus on that. It has this property of being APM. If for every integer, capital N, I can find some scheme, X, capital N, over mathfrak X, such that the following are satisfied. Firstly, the composition morphism from Xn to Y is projective. And secondly, that for every point in mathfrak X, the reduced cohomology of the fiber is all situated in very, very high cohomological degree. So if the reduced cohomology was to 0, you'd say that the fibers look like contractible spaces. That to ask that the fibers be contractible spaces is asking a bit much, but what we can ask is that the fibers look like contractible spaces up to some very, very high cohomological stuff. So a typical example of how you get a space that looks like this is take some incredibly high dimensional affine space, so AN for some huge n, and then just remove some very, very high codimension subvariety, like say a point. If I remove a point from A capital N, I get something that's homotopic to a 2n-1 sphere. So it has cohomology in degree 0 and cohomology in degree 2n-1, but I'm assuming that n is huge. So that's the kind of example to have in mind.
Ben, it's first time when the word stack appears in your slides. So you consider Artin stacks only? Or
and stacks. And in fact, for me, all stacks are global quotient stacks.
Oh, okay, great. And this notion, does it make sense for schemes of varieties? So it's really stacky.
It's really stacky, and I wish I could remember why it doesn't. Let's see.
Because your example with higher dimensional AN, it's not a stack.
Right. Yeah, but also the morphism from an minus a point to, say, a point is not projective. If you place both of these demands, that PQN is projective and that the fibers are nearly acyclic in this sense, if mathfrak X itself is a scheme, I'm not sure you get anything new.
Probably there should be theorem. The first condition is clear, but second is a bit kind of mysterious. Yeah, okay, but anyway, so it's technical question, but
okay, so what does this definition buy us? It gives us exactly this kind of phenomenon. It gives us a way to extend the decomposition theorem. So let F be a pure mixed Hodge module complex on mathfrak X.
Can you explain what the APM stands for?
APM is this definition here. APM.
I know, but the
approximately projective maps. You see, it's about.
Oh, I see. Okay, thank you.
Yeah. Okay, so let F be a pure mixed Hodge module complex. So here's the statement that if I pick capital N to be very, very large, then the natural morphism here is an isomorphism. So let me explain why that's at least why that makes some sense. It's that the pull back and push forward along Qn doesn't really do anything, except it's the identity in lowish cohomological degree. So if you think about it, it's adding in some extra cohomology, but in very, very high degrees, because the fibers of this morphism Qn look like, say, affine spaces with tiny bits removed.
Ben, I do not understand the notation. The morphism from what to what? It reads HI cohomology of this complex of sheaves.
Yeah. So I have a morphism of complexes of sheaves, and I take the ith cohomology functor applied to that morphism of complexes of sheaves.
What is isomorphism?
This morphism. So this now is a morphism of mixed Hodge modules.
Okay, all right.
Yeah, so I have, if you ignore the HI brackets, you have some, it's saying that this morphism of complexes is a quasi-isomorphism of complexes in low degrees.
Okay.
And here the capital N depends on the I, right?
Yeah. And it depends on F.
Yeah,
it depends on everything.
If you fix I, you should take N to be really large,
Yeah, and if F has enormous cohomological amplitude, then also you'll have to pick a much larger N. But the statement is that no matter what I you pick, no matter what F you pick, if you pick N sufficiently large, you can make this an isomorphism. But it's easy to show that the pullback of a pure complex is pure, so the pullback along Qn of F is pure. But then I'm taking the direct image of that guy along PQN, which I'm assuming is projective. So then by Saito's version of the decomposition theorem, this thing on the right is pure, which means that its ith cohomology is pure of weight I, which means that the ith cohomology of P lower star of F is pure of weight I, precisely because this is an isomorphism. So just knowing that your morphism is APM is enough to be able to extend the decomposition theorem. And also similarly, by playing around with these approximations, you can show that APM morphisms commute with vanishing cycle functors. And I just want to say in passing, this isn't such a strange thing to do. If you're familiar with the Borel construction of say equivariant cohomology as an algebraic variety, let's say we want to take the cohomology of point mod C star. The way we do that is well, let's say we want to get away from thinking about stacks. We say, okay, let's replace the point with a high dimensional affine space. The morphism from high dimensional affine space to a point is a homotopy equivalent, so that's fine. We take our high dimensional affine space modulo the scaling action of C star. It's still a stack, so we're still not there yet. But if we just remove the origin, then all we're doing is something of very high cohomological degree, and now we do have a variety. We have projective space. So in words, this tells us that the cohomology of point mod C star is approximated by the cohomology of projective spaces. And this is just a sort of general formalism that extends that. Yeah, but the punchline from this slide is that APM morphisms behave as though they are projective. Okay, so I don't know how far I'm going to get with this. It doesn't really matter. I mean, this is, yeah. So in order to do cohomological Donaldson-Thomas theory, I have to talk about quivers a bit. So Q is a quiver, which is algebra speak for directed graph, meaning I have a set of arrows, Q1, a set of vertices, Q0, and a couple of morphisms that take an arrow to its source and target. CQ is the usual free path algebra of Q over the field C. So the basis here is given by paths in Q, including paths of length 0 called EI, which begin and end at vertices I. Multiplication is just given by joining paths together if they will join together, and 0 otherwise. Dimension vector of a module over this algebra is just given by this tuple of numbers here. So one way to think of such a module is that you assign a vector space to each vertex and a linear map to each arrow of the quiver. And this tuple is just remembering the dimensions of those vector spaces. Like I say, all of my stacks are global quotient stacks. So here's one. MD is the stack of d-dimensional CQ modules where D is some dimension vector, and it can be described explicitly. I take this AQD, which is manifestly a space of representations of this quiver. And some of these are isomorphic, but they are only isomorphic if I can get from one to the other via change of basis. So I let this GLD act on this AQD, take this, the quotient, and that's my stack of d-dimensional modules for this algebra. In the background, and it's an important player, is the coarse moduli space, which is a slightly more down-to-earth object. There I just take the spectrum of the ring of GLD invariant functions on this AQD. And here the points represent, this is a less high-tech object. It doesn't really represent the functor as well as the stack, but at least points represent semi-simple CQ modules. I can say that much. And we're going to want to be able to take functions here. And here's how we do that. If you have really any elements of the free path algebra or of this algebra, I get a function on representations given by evaluating that element of the algebra. That element of the algebra gives me an endomorphism of the underlying vector space of my module, and then I take the trace. And that's called a potential. And up to elements in the commutator, it doesn't matter what I take. Okay, so that's just a little bit of quiver notation. Trying to think, where do I want to get to? So I only want to get through this slide. So the classic example, which hopefully illustrates some of what these objects are, is I let Q be the 3-loop quiver and set the potential to be X commutator YZ. So then MNQ is just the moduli stack of representations of the Laurent polynomial algebra in 3 non-commuting variables, where those 3 variables label the loops in my quiver. And yeah, the critical locus of this function, trace W, and this is a sort of not obvious thing to see, but possible to see thing, is given by the vanishing of these three matrix valued functions. So in particular, this thing which is supported on the critical locus is supported on the substack of representations of this free algebra, where all 3 of my matrices commute. I'm really looking at a mixed Hodge module on the stack of representations of the polynomial algebra in 3 commuting variables. And if I take the cohomology of that guy, if I take the derived global sections, this really is the sort of central object of study in cohomological DT theory of A3, of sort of zero-dimensional sheaves on A3. So that's the sort of classic example. Right, so I want to get through, I'm just going to skip forward to see, yeah, okay. So the key fact, which, yeah, I definitely need to get through, is that the morphism JH, which stands for Jordan-Holder, which is the morphism from the stack to the coarse moduli space that sends a representation to its semi-simplification, i.e. the direct sum of the subquotients appearing in one or any Jordan-Holder filtration. This morphism is APM. I don't know, once you see it, it's kind of obvious, and it's incredibly useful. But before you see it, it's kind of maybe a surprise that this is just always the case, no matter what the dimension vector, no matter what the quiver. And the proof idea, which I suppose I can go through this. The proof idea is, well, for the definition of APM, we have to introduce these auxiliary spaces, these spaces that sit above the stack and have smooth morphisms into the stack with almost acyclic fibers and projective morphisms down to the coarse moduli space. And those auxiliary spaces already exist in this theory. We take the moduli spaces of stable framed representations of Q. So that's a pair of a representation or a module F, along with what's called a framing. So a morphism from m-dimensional vector space into the underlying vector space of F, such that the image generates F under the action of CQ. And then it's just, it's easy to see, it's easy to see that the forgetful morphism is at least smooth with almost acyclic fibers. And also that the morphism all the way down to the coarse moduli space is proper, indeed projective. And that comes from some GIT. So the consequences are that essentially that the decomposition theorem holds for the morphism JH, which is a bit of a surprise because it's not projective. So it doesn't really fit into the specifications of the usual decomposition theorem. So in particular, if I push forward the constant sheaf, this is pure. The stack I'm pushing forward from is smooth, so the constant sheaf is pure. So when I take the direct image, it's pure. And also, again, by the splitting property of the direct image of the constant sheaf along JH, there's a perverse filtration constructed in the usual way on the hypercohomology of JH. And more generally, if I take the direct image of the vanishing cycles for any function, then this will split. This was something I explained very, very quickly at the end of one of my slides, that if I have a sheaf or a complex of sheaves such that its direct image splits, then it still splits even if I take the vanishing cycles functor before pushing it forward. And again, this just comes from the sort of general yoga of how these functors play with each other. So, yeah.
But this perverse filtration, I mean, you consider cohomology of a stack, which you can think of as equivariant cohomology.
Yeah.
Of this. Okay, what can be made kind of visible, this perverse filtration, or it's again some abstract thing which comes from, I mean, it's no easier than the general definition.
I'm not sure I understand the question. I mean,
The question is that if you have the cohomology, and for example, if your Q doesn't have loops, you can compute them explicitly, quite explicitly, yeah. And so you have some filtration, which you call perverse filtration. The definition was quite abstract. You should consider the stupid filtration, then take the image, blah, blah, blah. But in this particular special case of quivers, can it be described more explicitly?
Yeah, okay, so I'm at 50 minutes, so I guess I have to stop.
Yeah, but no, you can, okay, we can vote. I mean, if some people kind of have classes or whatever, they can leave. But I think you can continue and finish.
Okay. I mean, the last 3 slides are all examples, which I'm happy to just leave to people to go through it on that. So
okay, maybe you'll finish and then.
Yeah, I can try to finish. So the question is a good one and an obvious one, right? I mean, I've given this kind of very general abstract machinery for producing a perverse filtration on this object, but I've been quite shy of calculating anything for you, and it's probably not clear at all that calculating this cohomology is ever a reasonable thing to try and do, and also calculating this perverse filtration is ever a reasonable thing to try and do. And the rest of the talk is going to be a bunch of sort of big general theorems that tell us that these calculations aren't easy, but there are general theorems about them that make them a lot easier. There are general things that we can always say. So one thing I can say right away is that the perverse filtration always starts in degree 1, and we can describe the first piece of the perverse filtration very explicitly, and that will be part of what is coming up. So hopefully that will go some way to answering your question. Okay, so yeah, the answer is going to come out of something called the relative cohomological integrality theorem. And for that, I need a little bit of extra notation. So recall the points of this coarse moduli space represent semi-simple CQ modules, so direct sums of simple modules. So in particular, there is a direct sum map that takes me from a pair of such semi-simple modules and just spits out their direct sum. And this can be upgraded to a morphism of varieties. This is finite. This is a result due to Meinhardt and Reinecke, this lemma due to them. And so we define this convolution tensor product as follows. If you have a pair of complexes of mixed Hodge modules on the coarse moduli space, you take their exterior product, which gives you a complex on the Cartesian product of the coarse moduli space with itself, and then you just push it forward along the direct sum. You convolve them in this way. So I already highlighted that finiteness of morphisms is good for perverse filtration. So since this morphism is finite, the direct image with respect to it is exact with respect to the perverse T structure. So what this tells us, again, it's just a sort of formal thing, is that the Kunneth isomorphism between the left-hand side and the right-hand side respects the perverse filtrations on these two objects. If the direct sum map wasn't finite, this would actually fail. And so again, yeah, this is still more abstract stuff. So if I have an algebra object in this category, which means an object, a complex of mixed Hodge modules on the coarse moduli space, along with a morphism from the convolution tensor product of that object with itself back to itself, satisfying the usual associativity and unitarity axioms. Then when I pass to derived global sections, everything respects all of the perverse filtration. So this is a algebra object in the category of filtered vector spaces or filtered mixed Hodge structures, if you prefer. Okay, so the job is, what we're going to end up doing is building an algebra object in the category of mixed Hodge modules on the coarse moduli space. That's the goal. But to start with, I can just use this convolution tensor product to give the promised answer to Jan's question. So assume that Q is symmetric. If Q isn't symmetric, it doesn't matter, but there's some extra stuff we have to do with stability conditions that I just don't want to consider. So being symmetric means that there are as many arrows going from I to J as there are going from J to I for every pair of vertices. If I reverse the orientation of the quiver, I get the same quiver up to isomorphism. Then there is an isomorphism in this tensor category where the tensor structure is coming from this convolution tensor product between the derived push forward along the Jordan-Holder map of the vanishing cycles with respect to this function trace W for any W, it doesn't matter, and the following. I take the free supercommutative algebra generated by the thing in big round brackets. So the only, well, here I have the cohomology of BC star. So this is the usual cohomology of BC star, but this ver means I've shifted it by 1 by the dimension of this stack. And then this mystery object, the Bps Sheath. So yeah, I said it in words. The right-hand side is the underlying complex of this free supercommutative algebra generated by this guy. This is the important guy, and it can be given explicitly. The Bps Sheath is the vanishing cycle functor for trace W applied to the intersection complex for the coarse moduli space. So it's an answer. Actually calculating what this is in complicated examples is not much fun, but it's possible in some examples. So this talk in large part is meant to be an advert for the decomposition theorem and for semi-simplicity and all of these things. So let me just mention in passing that the proof starts with the fact that the direct image of the constant sheaf along JH is pure and thus semi-simple. So it uses the decomposition theorem in a vital way. I've already said it, but this object is called the Bps Sheath. And the theorem implies that the perverse filtration starts in degree 1, because in brackets here, I've got Bps lives in perverse degree 0. It's an honest mixed Hodge module. And then the only shifts are coming from the cohomology of BC star. And then because of this ver, I have cohomology in degrees 1, 3, 5, 7, blah, blah, blah. So the first non-vanishing perverse truncation of this is the first. It's degree 1 perverse truncation, and in degree 1 I just pick up these Bps sheets as I've written here. Okay, so it is possible to say at least something about this perverse filtration, and indeed to calculate what we get in nice examples. Okay, so yeah, okay, I can do this. As time goes on, I'm going to want to say more and more about geometric representation theories. So let's see the first algebra appear. So this guy, A tilde QW, this is what I'm calling the relative Kontsevich-Soegman coha. It's just the push forward along JH of the vanishing cycles complex. It's the thing that satisfies the relative integrality theorem from the previous slide. Now it's a bit late certainly late in the day for me to be going through all the nuts and bolts of this, but let me get it on the board. So we have this usual correspondence diagram. You consider the stack of all short exact sequences, and then you have 3 morphisms out, pi1, pi2, pi3, that remember the first, the second, or the third of these f's. And these fit into this commutative diagram. The fact that this commutes, let's see. Yeah, it's not saying anything very, very deep. It's that if I take the semi-simplification of an extension of 2 modules, it's the direct sum of the semi-simplifications of the modules that are extending each other. So that's fine. And there are just explicit morphisms of sheaves or mixed Hodge modules that we can build in order to give a multiplication, in order to give an algebra structure on this relative object, i.e. a morphism like the one that's just appeared here, from the tensor product of this object with itself back to itself. And you know, these might look more complicated than they really are. These really are just pull back, push forward along the morphisms in the top row of this commutative diagram. But the crucial thing is that if I apply the derived global sections functor to this algebra object, then of course I get a filtered algebra just in the category of graded vector spaces or graded mixed Hodge modules. So that's this thing in blue is the original Kontsevich-Soegman coha. And what I've hopefully demonstrated on this slide is that this coha comes with a natural perverse filtration because it lifts to a relative coha object. Okay, so let me see. Yeah, okay, so I'm not going to go through the examples, I'm just going to go through this side. So if I apply the derived global sections functor to the relative cohomological integrality theorem, which I will skip back and show you. If I take derived global sections of both sides of this big isomorphism, I get this isomorphism, where the BPS cohomology, this guy BPS, is just the derived global sections of the BPS sheath. This might not respect the multiplication, so that you might be wondering, well, I've now given you on the previous slide an algebra structure on the left-hand side. The right-hand side is the free supercommutative algebra generated by something or other, so for sure it has an algebra structure. Are they the same? The answer is no, and the answer is no in an interesting way. And here's the sort of payoff for keeping track of all of these perverse filtrations, is that if I pass to the associated graded with respect to the perverse filtration of the left-hand side, so remember this was a filtered algebra, then it does become a free supercommutative algebra, and this isomorphism that's starred becomes a isomorphism of algebras. So this tells us, I'm not really going to use this much, but it tells us that this thing satisfies a PBW isomorphism. This is sort of interesting always in and of its own, on its own, but it's a strong hint that this thing, it really wants to be some kind of quantum group. There's and because you have this cohomology of point mod C star here, it really wants to be a sort of Yangian of some kind, but that's not for this talk. But as a final bit of structure that you get out of all of this fancy footwork, since the perverse filtration begins in degree 1, and the associated graded with respect to the perverse filtration is commutative, that tells me that if I take the commutator of two things in perverse degree 1, they go to 0 in the associated graded, which means they go to perverse degree 1, which is just a long way of saying that the first perverse piece, i.e. this BPS cohomology, is a Lie algebra for the commutator Lie bracket on the coha. And this is the definition of the BPS Lie algebra. So I'm not going to go through any of the examples. They'll be in the slides. I've picked them because I think they're really illuminating examples, but I'm massively over time, so I won't get into them. But let me just sort of sum up by saying we've bought an awful lot of structure, an awful lot of very useful theorems on these cohas, and the way it's all gone is via the decomposition theorem. It's all come from proving that certain things fit, proving that certain complexes actually are semi-simple, so that we can actually calculate exactly what they are up to isomorphism. And the point of the subsequent talks is going to be to try to pull off the same trick, but in CY2 categories. So like categories of Higgs bundles, where it will be an awful lot harder, but maybe even more rewarding. Okay, so thank you very much for your patience, and I'll stop there.
Yeah, thank you very much. By the way, why did you call it integrality theorem, the one which you prove with Meinhardt? What is integral there?
Yeah. I mean, this is some, this is a very good question, and there is no good answer except that it's just a historical thing. So if you let's see, if you I mean, there is an integrality conjecture that one can extract from Dominic Joyce's work, let's see. What we prove is that, I mean, along the way, is that the function that he defines that he wants to be integral is the pointwise Euler characteristic of the BPS cohomology. So it's certainly integral. It's an alternating sum of integers. So yeah, it's not a very good answer. It's a proof of the integrality conjecture, but without any evidence of anything that could have been non-integral anywhere along the way.
But somehow you see, whatever your last theorem about this presentation of Coha as symmetric algebra, it's of course resembles classical result that the universal enveloping algebra of Lie algebra has a filter PBW theorem, yeah.
Yeah.
And then, but you can kind of whatever stays in the bracket and PBW, it's kind of a more integral object than the one on the left-hand side. So it's often defines over Z rather than over Q, even if the whole thing, the enveloping algebra is over Q.
Yeah. I'm nervous to work over Z.
Yeah, I
with
mean,
this stuff.
okay. All right, so more questions.
So Ben, did you say work over Z or?
Yeah, I mean, yeah, there are just lots and lots of different places where
I understand that if this works over Z, so that this is a sort of integrality. It's a kind of a integral form of the algebra.
yeah, I mean, the name really doesn't come from there at all. It's that
I see.
let's see.
Some sort of a constant Z form, or constant integral form.
No, there are the name probably is historical. There are some there were some conjectures. One, I believe, in our paper with Maxime, and probably in Dominic's papers. Something is defined over integers.
Yeah, I mean, if you look at if you try to define the BPS invariance via stable framed moduli spaces, you get the you get the certain partition functions are given by Euler product expansions, where the exponents are given by the things you want to be the BPS invariance multiplied by Euler characteristics of certain projective spaces. So the conjecture becomes the exponents, which you can prove are integers, remain integers even after you divide by the Euler characteristic of whatever projective space is in play.
And the Yunfeng is already left, but since he did some work on Gappa-Kumar-Waffe invariance, so this BPS, whatever, which is the name came from physics, is Bogomolny Prasad Sommerfeld, but the dimensions of this BPS, it's some invariance, so they kind of, these are Gappa-Kumar-Waffe, they should be integers. Yeah.
Yes.
So anyway, so it's indeed, it's kind of.
And also I have another question. So the BPS D algebra in general is just the super D algebra.
Yeah.
So there's no way to believe that it's honest D algebra.
So right. So in the next talk, I'll be talking about a very specific infinite class of quivers with potential given by tripled quivers with their canonical cubic potential. There, a lot of interesting things happen. One of them being that the Lie algebra is always even. It always lives in even cohomological degrees. But it's easy to dream up ones where you have an odd piece. So a nice example is what's called the non-commutative conifold, studied by, well, to start with Balázs-Szendrey in this context, but then lots of other people. There, the BPSD algebra has an odd part and an even part. And it's not even super clear how they interact. But yeah, it can be partly odd or entirely odd.
And also you use the on the stack, on the quotient stack, the constant shift virtual, suppose that's a smooth one. So just it's not the same as in the variety case, just as a constant shift.
Yeah.
The automorphism group acts. It's just the group acting on this constant shift trivial.
Yeah, you get right. The cohomology of the stack here is always just the cohomology of the BG, where G is the gauge group. So GLD, I think I was calling it, except that there's an overall shift by the dimension of the stack.
Okay, thank you.
Okay. More questions? So if not, no questions. So Ben, thanks for your nice lecture. We continue on Wednesday, same time. So.